parent functions, okay? This is the greatest integer parent function. So there's a parent function for every type of function, quadratic, cubic, square root, everything. It's just the simplest, most stripped down version. So don't multiply by anything, don't add anything. Just use that function on an input so we can see what happens, okay? So when we use this, to do this the first time, let's actually make, old school style, like input, output table, and look at what's happening, okay? So we said if you input 0, okay, meaning you're plugging 0 into the greatest integer function. In other words, you are calculating this. What do we get? 0, okay? Remember, integers are good. They stay what they are, okay? So 0, 0 is a point on my graph. What about when I plug in 1? Yeah, good, okay? The greatest integer function applied to 1 will still just be 1. So 1, 1 is a point on my graph. What if I plug in 2? Yeah, I get 2. Okay. Very exciting. Okay. Plug in 2, get 2. That's a point on my graph. All right, so I can guess if I plug in 3, guess what I'm going to get? 3. If I plug in 4, I'm going to get 4. 5, I'm going to get 5. Okay? I can see what's going to happen. And then the same thing the other direction. If I plug in -1, what am I going to get? -1. If I plug in -2, I'll get -2. -3, I'll get -3, etc., etc. So I know all of those are points on my graph. Can I just connect those with a nice line now? No. Okay? So here's why not. Is this function a linear function? No. Okay, why is it not linear? If it was just y equals x, we would connect these with a line, it would be linear. But those brackets have a meaning, right? This is a greatest integer function. It's doing something else to the input. So the question is, what kind of visual, what kind of graph is this creating? So let's look a little deeper about what happens when you plug stuff in between the points that we acquired. So what happens when I plug in 0.3? Yeah, 0.3 gets rounded to 0. Okay? So 0.3 comma 0 would be a point on my graph. What if I plug in 0.9? Yeah, it also gets rounded to 0. So we normally would want to round 0.9 to 1. Why are we not allowed to round it to 1? It can't be bigger than itself. That's what the greatest integer function does. Nearest integer, but not bigger than itself. Okay? So it also gets rounded to 0. So any number that I plug in that's between 0 and 1 is going to get rounded to what? 0. Until I reach 1 exactly, and then it reaches 1.
Check. Good morning, Oilers. We apologize for the interruption due to technical difficulties. This is John.
It's Ciara and Marcella with your morning announcement. I guess I should pause. All right, so here's where we were. We determined that we had all these endpoints, but we couldn't just connect them with a line because this was different than a linear function because those brackets were doing something different to the number. So then we determined we could plug in anything up until we got to 1 and it would still get rounded to 0. But then we already know that when we plug in 1, we get 1, right? Now, open point here because I can't really determine what the number is that's before 1. Does anybody know the number that is before 1? 0? What about 0.9? What about 0.99? Okay. So then we plugged in 1, we jumped to 1. So open endpoint right here at 0, 1 because we want to still be equal to 0 all the way up to the number that would be right before 1, okay? But there's no naming that number. Every time you guys say a number like, oh, 0.9999, Miss Dahl, like 0.999999. Like there's always another one in between, right? It's the weird thing about our number system. Infinitely amount of numbers between any two things you pick. Weird, right? So I can't say the stopping point, but I can say you go up until this, right? And then here's my filled in point. Now, if I start plugging in numbers that are between 1 and 2, like 1.4, what's that going to get rounded to when applied with the greatest integer function? 1. 1.9. 1. All the way until I get to the number 2, and then it will get rounded to 2. Right? So everything that's between 1 and 2 on the x-axis. When I plug those in, y is equal to 1 until I get exactly to 2. Sorry, my graph is small. I'm doing my open circles as best I can on here. And then you're going to have an open circle there. So what is this graph going to look like? Steps, okay? And let's make some notes right here next to your graph. Make some notes about the characteristics. So you expect steps, okay? Something else we want is we want like a starting point or a vertex point that we can kind of use for reference. This isn't a vertex like absolute value and quadratic. It's not technically a vertex because nothing like turns around there, maximum, minimum. But we're going to kind of refer to the vertex point, if I can write and spell, as being that starting point, that 0, 0. So that if our graph gets shifted up or down, we'll say, where does 0, 0 go? We'll kind of always use that as our reference, okay? So it's important to know that it looks like steps. It's important to know this reference point. The other thing that's important to know is kind of how the endpoints are set up and the length of each step and the vertical distance between the new steps starting. Okay, first of all, do any of the steps overlap? No, okay? But when one stops, does another one start in a new location? Yes. Okay, so that's important to know too. You're not going to have a step and then a giant gap in your graph and then another step. Okay? For every x value, there is some output. Okay? How long are our steps? 1 unit. Okay? And how far apart are our steps? Vertically. So here's a step. If I go that step and get to its end and I want to jump to the next step, how far vertically is that jump? 1 unit. Those are important things to recognize because those are things that are going to change when we change and start putting numbers in there. Okay? So we want to know the basic setup. So if I see this function, the first thing I'm going to do every time is I'm going to draw this picture. I'm going to have memorized that this picture goes with this. How I'm going to have it memorized, I'm going to know to start at 0, 0. And I'm going to know every step is a unit long and 1 apart. So I'm just going to go line, open circle, dot, line, open circle, dot, and make my little staircase. Okay? Are we good? All right, domain. What can be plugged into the function? Are there any limitations? Is there any x value that you're like, whew, Miss Dahl, if you plug that in, we can't do it? Is there anything? No. Even crazy stuff like pi. What would pi get rounded to? 3. Okay. So we can plug in anything for the domain. Okay, any x value you pick will have something on the graph. One note about these graphs, we don't draw arrows because the line doesn't go forever, but it's implied when you see the steps that they will continue. Does that make sense? We kind of have to just have an understanding about that because it wouldn't make sense to plot arrows on here. Okay, what about the range? Can you get any outcome? Somebody give me an example of an outcome, a y value that cannot be achieved with this function. You cannot calculate and get this as the answer. Okay. 2.5. Is there any time that you'll apply the greatest integer function to something and you'll end up with the outcome 2.5? No. What are the only types of outcomes that you are going to get? Yeah, integers. Okay, and if you guys remember, this is what we used for integers. You can write integers if you want. I live in the math world and I don't like to write things out. So are we good with the parent function? Yeah? So what we want to do is we want to establish some things that are going to happen. Some things are like absolute value. If I plug in a value for h within the greatest integer function, guess what it does? What did h do to your absolute value function? What's that? Yeah, moved it horizontally. Same exact thing here. No difference. Okay. What about k? Yeah, moves the y vertically. So what I do if a problem has an h and a k in it, like let's say someone gave me this equation instead of the parent function, instead of starting my steps at 0, 0 and following my pattern from there, where would I start my steps? H of 2, k of 1, 2, 1 is where I would start my step. That's why we're going to kind of refer to this point as the vertex, because we use that language with absolute value just to make it kind of transition better for you guys to recognize, that point is going to have the same implications that the h and the k had in absolute value. Okay. So if I was graphing this, I would go to 2, 1, That would be a filled-in point, but I would still make my steps. A unit long, open point, go up one, a unit long, open point. So is graphing these going to be difficult if I have the parent function memorized? No. Can it get a little crazier? Yeah, what if they put in negatives or multiply stuff by stuff? Yeah, life's going to get harder. But at least with this, shifting left and right, I should be okay. All right, so same application as absolute value. Does everybody understand that? And that was important. All right, so let's look at the negatives and multiplying by stuff and what happens. So two things can happen. We can apply the negative outside of the function, or we could apply the negative inside of the function. Okay? Which one of these, number 10 or number 11, does the negative affect the input of the function? Like it immediately changes the x value that you plugged in before you do anything else. Andrew. Number 11, okay? This is affecting the input, okay? In number 10, the negative is affecting the output. You were going to do that calculation anyways, right? That's what the greatest integer function does, but then you're slightly changing the output, okay? So let's look at what happens when we do that. So I have kind of a little cheat way that we're going to do it. We're going to let this graphing calculator on here do it for us. Don't look, sorry. Okay. All right, so floor is another rounding function that rounds down to the nearest integer, which is great, basically what the greatest integer function does, right? So this is like computer language telling it to do that. So A is the number multiplying in front of it. B would be multiplying x on the inside. And then you have your C and your D, which are like our H and our K, right? Shifting left or shifting right. Oh, that one's inside, so it's a little bit different. I don't know if I like that so much. But right now, I just care about A, and I care about B, okay? Because if A is negative, that's the negative outside of the brackets. If B is negative, that's the negative inside of the brackets, okay? So here's our greatest integer function. See how it looks just like what we graphed? Okay? See the red line, 0, 0. So what I'm going to do is let's make A negative 1, meaning the negative 1 is on the outside of our function. And look what happens. Okay? Now, what this graph doesn't show well are endpoints. So let's plot a couple of points by hand just to think about what's really happening there. So if I go to this graph where the negative is outside of the function, remember, that means the negative is affecting the outputs. Remember before you plugged in 0, you got 0. That's not going to change, right? Because 0 is not affected by negatives. That point still exists, okay? Before, when you plugged in 1, you got 1. You still get 1, but then you are multiplying it by a negative. So now when you plug in 1, you are getting negative 1. Okay. And what's going to happen when you plug in 2? You're going to get negative 2 instead of positive 2. When you plug in negative 1, the greatest integer function is still going to make it negative 1. But then because of the negative in front, the negative 1 is going to get multiplied by a negative, which is then going to make it positive 1. If you're unsure about which direction the steps go, like if you're right here and you're like, yeah, okay, so I know it should be steps because it's got the brackets. I know the other ends of the steps should have open endpoints, but do the steps go this way or do they go this way? Plug in something in between and figure it out. 0.5. So the greatest integer function will round 0.5 to what? 0. And then 0 will get multiplied by a negative, and then will still remain 0. So when I plug in 0.5, I get 0. What does it tell me? The step that is at this level goes this direction. I still know it's 1 unit long and 1 unit apart because that pattern hasn't changed. So my endpoint would be here. So this looks almost exactly like the graph that we had before. But it's that those solid endpoints look like a line with a negative slope rather than a line with a positive slope. Okay? So does a negative on the outside change your vertex point? Does it change the length of your step? Does it change how far apart your steps are? No, it just changes that after you draw that first step, instead of going up 1 to your next step, you would go down 1 to your next step. Everybody good with that? Okay, so you can make a note about that next to the graph, whatever you want to do. So let's think about what the negative on the inside is going to do. Okay, so you plug in 0. You apply a negative to it, it's still 0. Then you do the greatest integer function, and it is still 0. Okay, so again, that point does not change. Okay? What happens when you plug in 1? So I plug in 1, but because of the immediate negative, it becomes negative 1. And then I apply the greatest integer function, and I get negative 1. So 1 is negative. What's going to happen when I plug in 2? Negative 2. What's going to happen when I plug in negative 1? When I plug in negative 1, it's going to immediately have a negative applied to it, which is going to turn it into positive 1. And then I do the greatest integer function, so it will remain 1. So far, is this looking any different than what we had from the last one? No. Okay, so something that this has in common with that, we see the same change happening so far, right? Vertex doesn't change. Steps are still a unit apart both ways. Okay. Well, let's see what happens when we plug something in between. Okay? Let's say I plug in 0.5 again. This time the 0.5 is made negative before you round it. Okay? So when I plug in 0.5, it's multiplied by a negative, and now I want to apply the greatest integer function to negative 0.5. What do we get as a result when the greatest integer function is applied to negative 0.5? Negative 1. Good. Okay? Remember, it's between 0 and negative 1, but negative 1 is the smaller one, right? We can't pick the one that's bigger than our number. So this time when I plug in 0.5, I'm getting negative 1. That tells me that this step that's a unit long is not going the same direction that I saw before, right? Before, our step still went to the right, had endpoint, we just went down. Now I see that this must go like that if that's my outcome for 0.5. Okay, if 0.5 is on the same level as this must be part of that step. Okay? So then all my steps will then follow that pattern. So the good news is, once you've determined the pattern, you're good. The bad news is, this has a lot more involved than absolute value, right? Things are a lot different. They're not as simple as the absolute value function. It's a newer function to us. And we can't just factor the negative out or do something like that with it. It has a totally different application. So negative definitely changes our endpoints, that once we finish a step, instead of going up, we see it going down, right? Endpoint, go over and down 1. The negative on the inside causes 2 changes, right? The endpoints still go over and down 1 instead of over and up 1. And the steps are kind of in the opposite direction, like the endpoints kind of switch to the other side. Does that make sense to everybody? Okay, so this is something we're going to want to eventually memorize. If we see a negative there versus there, which way we're going to want to set up our steps. Okay? All right, the next thing that we need to look at is if we multiply by something on the inside versus on the outside, what changes does it cause to the graph? Okay? So remember, which one of these is affecting the input and which one is affecting the output? So out of number 12 and number 13, which one does multiplying by the 2 affect the output? Like after you already calculated the greatest integer function, you would just multiply it by 2. Good. Okay. 12, right? Because the 2 is after you already do the calculation. So this is like all the calculation you already did, but all the outputs you originally got multiplied by 2. Okay. So before, when we had 0, we got 0, 1, 1, and 2, 2, the parent function, right? This is basically saying, oh, take your original calculation and multiply all those outputs by 2. So 0 would still be 0, because 2 times 0 is 0. But instead of 1, what's this going to be? And instead of 2, what's this going to be? 4. So let's plot those endpoints. 0, 0, 1, 2, 2, 4, And again, since this is our first one, let's look at what's actually happening if we plug something in between. Okay, like what if I plug in 0.5, 1/2? It still gets rounded like it normally did. What does 0.5 get rounded to with the greatest integer function? 0. And when 0 multiplies by 2, it's still 0. So 0.5 is still going to be lined up with that 0. Okay? If you're unsure, you could do another one. Let's say you plugged in 0.9. Greatest integer function will round 0.9 to be 0. That will get multiplied by 2, which means it stays 0. Okay? Remember what happened before on our parent function. Everything that you plugged in between 0 and 1 got rounded to 0. So when those outputs get multiplied by 2, are they going to change? No. So they're still all going to get rounded to 0 until we get to 1. Okay? In the parent function, when we started plugging in numbers between 1 and 2, they were all rounded to 1. Okay? So they're still all going to get rounded to 1, but then they're all going to get multiplied by 2, which means instead of our step staying at 1, our step is going to be at 2. Okay? Because all of these inputs, 1.5, 1.9, 1.7, anything between 1 and 2, will get rounded to 1 and then multiplied by 2, which will be 2. So all of these will produce outcomes of 2, right? Until we get to 2, and then it's producing an outcome of 4. So here's the pattern of our steps that's happening now. So somebody summarize for me what multiplying by a number on the outside, or multiplying the output by a number, okay, what is that doing to our parent function? Yeah? Good. So the vertical gap between steps is going to change by that number, right? It was 2. Now our steps are 2 units apart. If it was 1/2, how far apart would my steps be? 1/2 a unit. This step would end, and 1/2 a unit above it, the next step would start. Okay? If it was 10, how far apart would my steps be? 10. I would draw one step. It would end. 10 units above it, my next step would start. But my steps are still a unit long, right? It hasn't done anything horizontally. Because this multiplied the y-coordinate, and the y-coordinate is about the vertical stuff, right? When we move over here to number 13, this 2 is going to multiply the x-coordinate before you do anything. So it's going to mess with the horizontal stuff because it's basically changing your input immediately. Does that make sense to everybody? And so let's plug in some stuff and look at what that looks like. We'll do some of the same things as there. So like 0, 1, 2. All right, so you plug in 0. 2 times 0 is 0, and the greatest integer function rounds that to be 0. All right, so 0, 0. Notice, has our vertex changed? No, so this is really good. If the vertex doesn't change, you notice still plot this first step here. You just have to draw your next one further away from it vertically. Okay? Here, let's see what happens. So when we plug in 1, 2 times 1 is 2, and then that gets rounded to 2. And when we plug in 2, we get 4. 0, 0. So this doesn't look any different, right? Let's see what's happening. Right. Let's plug in 1/2. Okay? So this is really interesting because when we plug in 1/2, the 0.5 is immediately multiplied by 2, which turns it into what? 1. That's super interesting because then the greatest integer function will round that to be 1. Is that the same as either of the endpoints that surround it? No. So because there are numbers between these endpoints that when multiplied by 2 become a new whole number, they're creating a new endpoint for a new step because we're getting a new whole number inside of the brackets, right, that didn't have to be rounded. So at 1/2, I'm actually at 1. Okay. What am I going to be at when I plug in 1 1/2? 3. Any idea what this 2 is going to do to our parent function? Sure. Yes. Okay. So the intervals, instead of them being 1, or the length of our steps, instead of it being 1, the length of our step is going to be 1/2. Okay? So a little bit tricky. Why 1/2? It's the reciprocal of 2. Okay? So I would make a note next to this graph that multiplying by something inside the brackets here changes the length of my step. And basically, the length becomes 1 over whatever that value is right there, right? It didn't become 2 units long. It became half. Okay? So what if this had been a 5 right here? How long would each of my steps be? A fifth of a unit. It would be super hard to graph, I think. Really big scale stuff, right? What if this number here wasn't 2 but was already 1/2? How long would our steps have become? Not 1/4. 2. Yeah, it's always taking the reciprocal. 1 divided by 1/2 is really the same thing as 1 times the reciprocal of 1/2, which is 1 times 2, which is 2. So putting this 1 divided by that number, if it's a whole big number, our steps get smaller and smaller and smaller, right? So the bigger the number gets there, our steps shrink and get smaller. The smaller the number gets, our steps get bigger. If this was 1/12, how long would our steps be? 12 units long, right? Super long steps, okay? But the distance between each step is still 1 unit. So I draw a step that's half a unit long with an open endpoint, doing the best I can on my graph, sorry. Jump up to the next, still 1 unit apart vertically, and draw the next step that's half a unit long. Jump up 1 to the next step that's half a unit long, etc. And once you've drawn your first step and the one adjacent to it, you can just do the pattern forever, and you have your graph. Okay? All right. So take a minute in your groups, and that is this. See the 2x minus 4? Remember in the absolute value, we factored the 2 completely out of the brackets? We can't do that here because when the 2 changes the number inside the brackets, it might change the way that it's rounded, right? So we can't factor it all the way out. But we do know that if the 2 is in here in the brackets and there's other stuff, is that 2 affecting more than just the x? It's also affecting why this number looks like 4, okay, because there's a 2 multiplying through everything in that bracket. So when we see the equation, the first thing we want to do is we want to factor that coefficient of x out, but not all the way out like we did in absolute value. This function doesn't have the same, it's not as simple as absolute value, right? It's a lot more complicated. So we can't take the 2 all the way out. But the reason that we want to look at it like this is now you can see your h and your k. Because remember in our h and our k formula, it only existed when you had x minus h. Did it say you could have 10x and it was minus h? No. Okay? So in order to see what the h value actually is, you can't have a coefficient on x. So every time we're just going to rewrite the inside by factoring this out. We won't do what we did with absolute value and get it all the way out because that's not possible here, but we can at least see things a little more clearly. What is my h value then? 2. And my k value? 1. That means the main vertex of this graph, the starting point, when I start my first step, am I going to put it at 0, 0? No. Where am I going to put that point? 2, 1. So I'm going to start my very first step at 2, 1. Okay? All right. No negatives are in our equation. I'm very excited about that. I don't know about you guys. That's the hardest part, right? The visual of what's going on with those is pretty difficult. Because the other parts aren't that bad. So, Michelle, tell us again. What does the 2 tell us about what's happening in this problem? Good. So this tells me the length of the step, so the actual step, is going to be 1 over whatever that number is, which happens to be 2, half a unit long. So each step I draw is going to be half a unit long. Since there are no negatives, I know which direction to draw my step from this starting point. Do I go to the right or to the left? To the right, right? They all did until like the negative was put on the inside and it did this weird whatever, right? So I know that my step is going to go half a unit long and end right there. Right? How do I know that? I knew my starting point, and I knew how to interpret this number as the length of my step. Okay? All right, and then Samantha told us the distance between the steps, which was what? 3, because of the 3 multiplying out here. So this is the vertical distance between the steps. Do I have to put 1 over that number? like I did here? No, it's just 3. Okay? I know that's super weird. It has to do with the fact that the 2 here changed a number before you did the crazy function stuff to it. The stuff outside is much simpler because it just took the regular calculation you got and then like multiplied it by something. It's kind of like H and K. H is all complicated, right? Because it looks like -2, but it shifts to the right 2, right? But K is much more straightforward. You took what you got and you added 1 to it. You literally went up 1. That's all. Okay, so the stuff outside the function is usually a lot simpler than what's happening inside the function. Okay? So the distance between my steps is 3 units. So I know that I need another step to start where this one ended as far as x goes, so like at 2.5. Okay? And it should start 3 units vertically away from this step. Below this step or above this step? Above. It should follow the normal pattern because no negatives were applied for any sort of like reflecting our staircase the other way, right? So 3 units above this, 1, 2, 3. I'm going to put my closed endpoint where that open endpoint ended. And I'm going to draw my second step that is half a unit long, right? And then it will end right there. Could I then, from having these 2 steps, fill in the rest of the graph with the pattern in which the steps will follow? Yes. Okay? So I'm going to fill in one more this other side just so it looks very complete. 1, 2, 3. Open. Closed. Okay? I'll even do another one. All right. Aren't we happy we figured out what the numbers do rather than try to plug stuff in there, round it, multiply it, calculate it, do all. I mean, if all else fails, you could do that. But are you always going to find your endpoints really quickly by doing that? Probably not. You'd have to plug in those perfect numbers that round to whole numbers and all this kind of stuff. And if someone put fractions in there, that could get a little bit complicated, right? All right. Let's do one more. Oh, negative. Darn it. All right, so first thing we want to do, even though this is just a negative, and you guys are like, that's not a number, this negative has affected everything in here by being part of this. So anything that's in front of x, a negative, a number, whatever, needs to be factored out. And when I say factored out, do I mean all the way out of the greatest integer function? No, but rewrite it so you can clearly identify your h and your k. So we're going to say that this is f of x equals 1/2 times, and inside the greatest integer function, I'm going to factor out the negative, which is going to leave me with x minus 3. All right, in your groups right now, determine the first point you plot on this graph will be where. That you would start your graph. 3, 0. Good. Okay. So hopefully this was determined is because our h value is 3, right? And our k value, since there's nothing being added onto this equation, is 0. So we think of that vertex point. Remember, I'm using that term very loosely, okay? I'm just trying to use one word that always describes for us the starting point as 3, 0 from our h and our k values. Good. 3, 0. Okay, what does this negative tell me about the appearance of this graph and how I need to build it? Yeah, so instead of going to the right, the steps are going to go to the left, okay? And the other endpoint is going to be down and to the right of this, or if you go to the left, you could then go up. So the endpoints are going to look like a negative sloping line rather than a positive sloping line, and the steps aren't going to go to the right from the closed endpoint, they're going to go to the left, right? This negative inside, remember, did like 2 switches, right? It switched our endpoints from appearing like this to appearing like this, and then our steps, instead of going this way, to look like they're going that way, okay? The negative on the outside would have only changed this appearance to this, but it still would have looked like our steps were going to the right, okay? Again, I know that that's complicated and hard to remember, but it's easier than plugging in a million points to try and get the endpoints on the graph, okay? So I know that I'm going to build my step towards the left to put the endpoint, okay? How long should my step be? 2 units. No. Close. I know what you're looking at. Not a bad idea. 1 unit. Why is the step length not going to change? Good. This is a -1. So the negative has its own effect But inside the function, which is affecting the horizontal stuff, therefore the length of our step is still a 1. So yeah, you can put that under 1, but 1 over 1 is still just 1. So our step length horizontally is still 1. There was no number value multiplying x, only the negative, right? So the negative changed the kind of directional approach that we're thinking of it, but the number part didn't change. Therefore, horizontally, your step was not stretched or compressed. It is staying the exact same size as the parent function step. Okay? So what does then the 1/2 tell me on the outside? What does that tell me? I see Lauren. Yeah? Mm-hmm. Good. The vertical separation between steps. So when one step ends, the next step should be half a unit away from it vertically, my next beginning point. Okay? So steps are still a unit long. Okay? And then the next step should be half a unit away from that. Now think about what the appearance that you want your steps to be as you decide, do I go half a unit above or half a unit below? That negative should make your staircase look like it's having this negative slope rather than this positive slope. So should my next closed endpoint be above or below? Above, so that when I draw the next 1 unit step, it fits that image of what's going on here, right? And the endpoints, so the negative thing, remember, check it twice. No matter where the negative is, you should kind of have this appearance, okay, going down as you go across the graph. The negative being on the inside should add this extra appearance of the endpoints and opened endpoints kind of being reversed of how we thought of them before, okay? So then I could continue that pattern every half a unit above another step that is 1 unit long. Is this okay with everybody? Right, so this is going to become really important in our course. Basically, every function we learned, and the absolute value still has all these same characteristics. Okay? The number outside, it wasn't steps, but the number outside still affected how far above or below the vertex you drew the next point, because it was like slope for us. Every function we learn is going to do this same idea, and this is the first place we're really seeing it. And when this unit ends, we're going to put it all together and learn the proper language for it and everything to apply. But right now, with the step function, we will just refer to each step. Okay? Any questions?